Hello, my name is Bu Liu, a junior at the International School of Beijing, and my future intended major is geophysics, particularly hazard prediction. So today I'm going to present my topic, predicting California's seismic hazard based on the effects of crustal elastic response to seasonal alteration of shear stress change and regional fault lines. So a summary of the research topic is that California's transient crustal string responds to hydrological loading and seasonal column stress change. So the particular reason that I have choose California and Sierra Nevada region is that California is a state that is designated for its spectacular geology oddities. The topic has been on debate for decades, and it is mainly about the credibility of the measurements such as cGPS or GNSS. But the main inspiration is that the disaster movies on the big one that I have watched in the past years, which demonstrates a hypothetical earthquake that might occur in the California in the future. And hence, I would like to use this study to propose various hazard prediction methods in the future. So, my instructors are Professor Sidney R. Hemming from Columbia University and Professor William E. Hott from Stony Brook, as well as Professor Troy Raspberry, who's also from Stony Brook. And initially, Professor Sidney Hemming discovered that I am interested in the geophysical aspect of it. Hence, she decided to find two assistants, which are the other professors that are in the list, to help me plan a good topic. And initially, I believe that I will keep my topic into volcanoes, which Professor Raspberry proposed Mexican volcanic belt, which includes El Popo, Volcán Colima, etc., as well as the Jalisco region, which form as a result of volcanic activity and subduction. Nevertheless, I found the seismology aspect more appealing and has a prediction. As a result, both Professor Hemming and Professor Holt decided to propose the topic of Sierra Nevada and seasonal stress change after discovering my interest in geophysics and inversion. And they have proposed various past papers, such as Kim et al. And Kraners et al.'s paper, which discusses the Ridgecrest earthquake as well as the South Napa earthquake. And both has interpreted from the hydrological load aspect as well as the seasonal alternation aspect. So my independent variables that I have taken into account are horizontal displacements from cGPS, otherwise known as the Continuous Global Positioning System in mm, Coulomb stress change in kPa, and tectonic stress load in kPa. The picture to the right is a map of GNSS station scattered across the state of California, which has also labeled the epicenter of the Ridgecrest earthquake in 2019. The methodology and techniques that I have used. I have referenced the Kim et al. Papers, which he both proposed in 2020 and 2021. Crustal string patterns associated with normal drought and heavy precipitation years in California was the 2020 paper, which states that greater horizontal displacement towards Sierra Nevada during heavy precipitation winter was detected. While for the 2021 paper, repeating non-tectonic seasonal stress changes and the possible triggering mechanism of the 2019 Ridgecrest earthquake sequence in California, the conclusion is that the Ridgecrest earthquake was combined effect of seasonal column stress change, which peaks around May and June, as well as a 1.4 kPa tectonic stress increase in the Eastern California Shear Zone on an annual basis. I've also referenced the 2018 Craner et al. Paper, which entitled The Seasonal Non-Tectonic Loading Infer from cGPS as a Potential Trigger for the Magnitude 6.0 South Napa Earthquake. And the horizontal motion of cGPS suggested that there is a seasonal variation in the region surrounding the epicenter, and which can be seen on the figure to the right. And it is associated with a Coulomb stress change in the nearby right lateral fault, which is also labeled on the screen. Moreover, I decided to contrast the precipitation in Sierra Nevada in winter to compare the seismic patterns. This is a late winter of the Sierra Nevada in 2017, which was considered pretty low precipitation as Mono Lake is exposed. And there was a heavy precipitation in 2019 where the Mono Lake area is completely covered in snow. And it has as a result, the magnitude 7.1 earthquake had occurred after the snow melts. But the contrasting point of this is that last year was also a heavy precipitation year, but an earthquake did end up without occurring. So I decided to take a mathematical approach which reconstructs Kim et al.'s model. And this is a model that Kim et al. Has constructed in 2021 paper. And some of the given value is that the seasonal stress variation is at 0.7 kPa on an annual basis. And the stress variation period, given that there's only one peak around May and June, I decided to assume it is 0.5 years. And the tectonic stress increase rate is 1.4 kPa per year. And I have assumed a 12-year time span, which measures from 2007 to 2019. As a result, this helps me to construct a sinuendo graph, as 0.7 matches the amplitude, the 0.5 matches for the 2, which is the period, and this 1.4 kPa per year matches a linear increase in the steady state tectonic stress load. And T would be placed between 0 and 12, which measures from 2007 to 2019, which measures the total stress load. As a result, the plot constructed is that there will be a peak every time around the year where there will where the total stress load peaks until it surpasses around 16 kPa in 2019. It has the 7.1 magnitude event has erupted. So the conclusion that I draw from this study is that hydraulic load and seasonal stress variation could influence the regional seismic patterns in Eastern California Shear Zone, albeit subtle. And the combined result of seasonal stress change and a constant tectonic accumulation could affect the occurrence of right lateral events, such as the two events occurred in 2019 and 2014. The seasonal stress change is a crustal elastic response in the Eastern California Shear Zone after snowmelts from the nearby Sierra Nevada range. And more massive hydrological load could lead to greater shear stress change in the region, which causes a higher chance of a major earthquake. A few future prediction methods are InSAR and GRACE, and InSAR refers to the interferometric synthetic aperture radar, which used for mapping ground deformation using surface images. And it has been adopted by the European Space Agency Sentinel-1A satellite, and has been confirmed accurate in measuring crustal strain movements in the South Napa region since 2015, according to Craner et al. It has an accurate identification of spatial pattern, horizontal, and vertical motion. And on the other hand, the GRACE MASCOM method refers to gravity recovery and climate experience mass concentration. It is accurate in measuring seismic deformation, especially at the equator. It is accurate as it could construct a 1 degree times 1 degree grid map. And it has been successfully predicted the magnitude 8.8 Chile earthquake as well as the 2011 9.0 magnitude Tohoku earthquake. It can investigate a seismical cycle through a version of the seismic parameters. So the two main challenges that I have faced is that there are debates over the accuracy of InSAR data in these papers, and as well as the questions on the subtle effects of hydraulic load on shear stress in ECSZ. And and I have attempted to simulate these in Python to support Kim et al. But I found that there are solutions to these. I decided to combine all the previous research and came up with a plausible conclusion that has a combination of mainly both Kim et al. And Craner et al. Paper. And I found Kim et al. Paper to be the most reliable explanation. And for the second obstacle, I decided to address using a cross-disciplinary approach, which is the construction of the sinusoidal graph, and considering the given variables that I have mentioned in the previous demonstration from Kim et al.'s 2021 paper. Some of the takeaways. So cross-disciplinary thinking is the key to success in STEM objects. It is especially important in the field of geology, as I recognize that the topic itself is considered cross-disciplinary because the since the association between climate and seismic activity is too subtle, so it is hard to consider these unless there's a closer observation. And the second is a personal advice that I would suggest to everyone who's interested in geology, which if in the evaluation of an expert method, we should consider the accuracy of the method, the organization that are currently involved, as well as its relevance to the investigation. And geophysics is a long-term investigation. It is not a subject that can be completed in short years. Given that the InSAR around the South Napa region has only launched in 2015, so there's no direct evidence to conclude that whether Craner's conclusion on what caused the 2014 South Napa earthquake is right. And the influences of the project on me personally is that I will become more aware of the GNSS stations as well as surrounding landscape while visiting, especially when visiting places such as Yosemite, right in the Sierra Nevadas. If there are a lot of snows, I will consider when there will be the next earthquake. And I will also further consider the credibility of these prediction methods when taking a look at these data in the future when I get into work. This GRACE and InSAR data are really useful in supporting all of my methodologies. And I will become more cautious around my surrounding environment in the future college research, as given the unstable nature of of tectonic plates. Because an earthquake can definitely occur without any warning, even without a stress measurement of stress change, which could completely contradict the outcome of this study. Thank you for listening.